Now, to be very honest, I am rather ashamed of myself for really using contour integration so late in my solving integral sort of journey. And this is kind of the type of integral that was sort of missing out when I wasn't doing it. Because here we have from negative infinity to infinity over the entire real axis, the integral of sine x over x squared plus x plus 1 dx. Now, this function, using normal means and normal bounds, is practically impossible. There is no way to calculate it, I believe, using standard functions, which is why contour integration comes into play here. So, first thing, what we're gonna do, I'm gonna sort of rewrite this because sine is basically the imaginary part of e to the ix. So we can rewrite this as the imaginary part of the integral from 0 to infinity of, no, not 0 to infinity, negative infinity to infinity, of e to the I times x over this x squared plus x plus 1 dx. Okay, so now we have that done, and now I'm going to consider the complex plane, and more specifically, we're going to integrate over a certain path, and this path is going to look like a semicircle on the positive axis, essentially a sort of semicircle there. I'm bad at drawing semicircles, apparently. With the radius infinity. So this is infinity, this is positive infinity. Okay, so we're gonna call this big contour, this big integral, this big path, big gamma, and then for this semicircular arc, we're gonna use little gamma. Right, so this is now equal to the imaginary part of the integral over this big contour gamma of this e to the I x over x squared plus x plus 1 dx, and then minus the integral over the small contour gamma of that exact same expression, e to the ix. And now, one small thing to notice here is that this sort of contour, small gamma, it lies infinitely far away. So you could say that this is basically I times infinity, or infinity plus infinity I, or something like that. But if you were to really plug this in, you would get e to the I times infinity, which would just end up to be, well, it would end up to be e to the negative infinity, which is going to be 0. So in theory, this entire bit over here is just going to be, well, the contour over a function that is just 0, because, well, every single value is 0. So essentially, this entire thing, well, it's going to be 0. And so you could just ignore this entire bit. Now, normally there will be some more mathematical works to, demonstrate this process, but I think it's better if I just talk it through. It might actually be better to understand or easier to understand than before. Okay, right, so now all we have here is the imaginary part of the contour integration over this big gamma, this full semicircle, e to the ix over x squared plus x plus 1. Now, as in regular contour integration, and as I have found out, you basically just have to use the residue theorem. That's what it's called. You have to use the residue theorem. So what this says is that, so a residue is basically, I actually don't know how to describe it. You'll figure it out. So now, first of all, we have to figure out the roots of this thing, because residues rely on the poles or the asymptotes of the function. So now we want to find the complex roots for which x squared plus x plus 1 is equal to 0. This is pretty easy. I mean, maybe you already know the answer. It's something related to the golden ratio. This is going to be x is equal to, so negative b, negative 1, plus minus the square root of b squared, so 1 minus, and then 4 times, never mind, it has nothing to do with the golden ratio, apologies. Okay. So we have these two numbers, which we can write as root 3 over 2 times I minus 1/2, or root 3 over 2 times I, well, negative minus 1/2. So these are the two solutions. And now basically you want to pick the one that lies within this contour, which is basically in the top half of the complex plane. Now, to let that work, we have to set the imaginary part here to be bigger than 0, and this thing is going to be ignored. So all we really need is to figure out the sort of the residues for x is equal to this value right here. So I believe it's denoted with res, but I'm not really sure, of this e to the I x over x plus x squared plus x plus 1, and then we have over here e to the I x. And then I'm going to make up some notation here. We're going to say x is equal to this chunk. I am fully aware that the camera's quality might not be able to record this, but yeah, well, whatever, okay? So this is equal to the limit as x approaches to this exact same value. So we have root 3 over 2 times I minus 1/2. Once again, if the camera quality is too bad, don't blame me. And then we have, so first of all, this polynomial expression can be factored as this x minus root 3 over 2I plus 1/2, also times x plus root 3 over 2I plus 1/2, yeah. And then over. Now, we do with the residues, you basically plug in x minus this value. So we have x minus root 3 over 2I plus 1/2, and then e to the ix. And then these two cancel out, and then you realize that there is no asymptote, so the limit is just evaluating this at this point. And so we get that this is equal to, let's see, root 3 minus okay, so minus 1/2 plus 1/2, that will go to 0, and then we have root 3 over 2 plus root 3 over 2, that's going to be root 3 times I, so we have e to the I, and then we have root 3 over 2I minus 1/2 over, and then we have this root 3 times I term over here. Ready, so this is basically the value of our residue, and then it would be easier, because technically we are taking the imaginary part of this entire thing. It would perhaps be easier if I were to sort of write this using Euler's formula. So first of all, root 3 times I, that is equal to negative I times 1 over root 3. I think that is correct. Yeah, negative I times root 3. And then this one is going to be, so first of all, if I were to distribute the I, I would get, that's the terrible joke, I times root 3 over 2I is going to be negative root 3 over 2. I don't know why I said 2 like that. And then it's going to be I times basically this thing. So we have minus 1/2 I. I believe, I hope I am right. So basically, what we have now, we can drag this e to the negative root 3 over 2 out. So we have e to the negative root 3 over 2. And then we have this e to the negative 1/2 I, which we can use Euler's identity, which would mean that that is now equal to cosine of negative 1/2, which is just cosine of 1/2. 1/2 radians has no closed form. I don't think so. I mean, in terms of degrees, that is, or the cosine of which. Never mind, ignore that. And then we have plus I times the sine, but sine is an odd function, so this negative goes out front, so we have negative I times the sine of 1/2. There you go. And then, okay, so now I'm going to distribute the I to these couple so that we have a general idea. I don't know why I'm saying things. Negative root 3 over 1. 1 over root 3. E to the negative root 3 over 2. And then, okay. So now we have I times negative I is going to be equal to 1. So we just have sine of 1/2. Okay. And then I times this thing is just going to be plus I times the cosine. Right, so here we have the residue, and I'm going to erase this because we need space. So the residue theorem says imaginary part. Now, the residue basically says that the integral is equal to 2 pi times 2 pi I times the residue, which is going to be, you know, I might as well just distribute 2 pi I into it. It doesn't really matter. So we have maybe we should distribute this while we're at it as well. So we have negative. I'm gonna use a parentheses. So we have negative here, negative 2 pi 2i pi, and then over root 3. And then we have e to the negative root 3 over 2, and then the sign of 1/2. And then, okay, so distribute this, negative and negative will mean negative, so we have minus again. And then 1 over 3. Oh, wait, no, 2 pi. And then it's supposed to be I, but we have an I over here anyway, so I negative 1, so this is going to change to positive. And then 2 pi, and then we have the same thing, e to the negative root 3 by 2, and then the cosine of 1/2. It really doesn't matter what the second half of this entire term does, because, well, we're looking for the imaginary part. We don't really care about whatever this is. This could be, I don't know, pi squared by 2 for all we care. And then, well, the answer is right there. It is going to be equal to negative 2 pi times over root 3 times e to the negative root 3 over 2, and then sine of 1/2. And that's the answer. So, from this result, I kind of felt disappointed that I had missed out for so much, because this result is actually kind of interesting. It's very interesting, and to be fair, this result wouldn't exist if it were not for contour integration. Now, one might say you might compute this with brute force, and you're more than likely to try. Although I'm not going to try because, well, I have limited time. So I feel like this is very interesting. Perhaps I'll do more contour integration, and perhaps I'll do something similar to this. Maybe someday in the future when I get more nice results. Well, that's it for this 2 weeks. I was gonna say I was gonna upload in 2 weeks' time, but now I realize that's probably not possible. So I'll see you whenever I next upload. Okay, see you guys later.